Okay, this is the graphing review. Graphing is kind of different. It doesn't use so many formulas, but it does require an understanding of the other formulas that we're using. And so, whoa, let's get started. This is page one. The first question is about a nervous science student who paces back and forth in front of a teacher's room waiting for his exam to be over. The door to the classroom is the origin of motion. Okay, so we're going to use this is our information that we are using here. Okay, and we're going to start at time zero. Oh, this is time zero. The student is 3 meters to the right. So remember that we decided right is always positive. Okay, and so our position is 3 meters. It already says meters there, so we're good. At time 5 seconds, the student is 2 meters to the left. 5 seconds, we're at minus 2 meters. Okay, and at time 8 seconds, 8 seconds, so that's here, we're at 6 meters to the left. So that's minus 6 because left is minus. Remember that, left minus and right is positive. At time 12 seconds, the student is 4 meters to the right of the door, so it's positive 4. So we always need a time and a position when we're doing graphing. A time and a position. We have all these pairs. Okay, so now we can kind of ignore all the writing. It's hard to sift information from there, but we did it, but it's in this table now. So now we can mark it on this motion line. So time zero, we're at position. So this on the bottom marks our position. Okay, and so why don't we say this? This is our position in meters. That's what this is showing. Zero is the door. Okay, so we can imagine this is the door to the classroom, and that's where the student is pacing back and forth from. And so we want to mark where is the student at the various times throughout this story. And so at time zero, they're at 3 meters. So remember, these numbers are the meters, and so they're 3 meters at time zero. So t equals 0. And so we have to mark both of these. We have to mark the position at 3 meters and the time for each point. And so the next point is going to be at 5 seconds. We're at position minus 2. And so let's do position of minus 2. That's right here. And we also have to mark the time. So remember, this is the position down at the bottom, and this is the time. So t equals 5 seconds is when we're at minus 2. And then finally, we've got, thirdly, we've got 8 seconds, position of minus 6. So position of minus 6. And we also have to mark the time. T equals 8 seconds. And now finally, we're at positive 4, which is right here. And that's at a time of t equals 12. So always marking the two things. Where I like to end is I always like to draw arrows. So we started here at time equals 0 and we walked till there. So I do an arrow and then we walked till time equals 8. Like we can figure this out without doing that. And then we did an arrow from time equals 8 all the way over here to time equals 12. That gives us a good representation. But doing this is done. Boom, check mark. That feels good. Give yourself a check mark. Try this graph on your own, pause the video, try it out, and see where you get. All right, this is putting it all together. Remember, this is 3 different ways of doing the same thing. Okay, the points that we want to look at are 0 and 3 when time is 0. So we've got time on this axis. So moving forward, it's time. Position is up and down. So positive up is right and down is left. So remember that. Up is right, so R for right. And if we're going down, we're going left. All right. And so where do we start? I like to start off by plotting my points. Okay. At 0 seconds, we were at 3 meters. At 0 seconds, this is 0 seconds. This is 3 meters, so we're right there. And then we walked to, at 5 seconds, we were minus 2. So where's 5 seconds? That's our time, right? And our time here should be in seconds. Nice fat pen. That was terrible. Okay. Let's do this, make sure we know this is in seconds. At 5 seconds, this is 5 seconds here. Okay, between 4 and 6, we're at minus 2. So I'm going to mark that spot. 5 and minus 2, right? And then we're at 8 seconds, we're at minus 6. So here's 8 seconds, and we're going to go all the way down to minus 6. And then finally, at 12 seconds, we're at plus 4. Plus 4 is way up here. 12 seconds, we're at plus 4. That's right there. So now we've got all of these things. Now I like to just add lines. And so you'll shape lines. And it's pretty simple. You just connect the dots. Once you've got your dots, this is not too crazy. You just connect the dots in order. You can never go backwards in time, so we got to keep moving forward. This is done. Let's give ourselves another check mark because that feels good. Big fat check mark there. That's awesome. All right, next question. Try this question ahead of time. Try this without me, okay? What you're doing is just marking down this line from the graph. Okay, hopefully you paused it and tried it. What we're looking at is the position time graph shows the particle moving along a number line during a period of 12 seconds. So you use the graph showing the motion to do the rest. Show the position of the object with a dot at each important time. So pretty simple start. The important times are here, here, here. How am I picking these? Just randomly? No, I think you see them right away. They're each intersection or corner where something happens. So we used a dot and we marked the important sections. Now, let's label each dot with the time it was at that position. Okay, and so I'm just going to do text here. This is 0 seconds. T equals 0. This down here is t equals, what is it? Time here, 4. Okay, t equals 4. And here we are at t equals 5, t equals 8, t equals 10, and t equals 12. And now what we're supposed to do is we're supposed to be doing this on this line down here. And so we can transfer this, but notice that this is position here, okay? But now our line is doing position horizontally. Probably in meters, yeah. And so we got to transfer these dots over there. So it looks the same. So we see at t equals 0, we're at minus 10. And so we're going to do the same thing, minus 10. Now we're going to say this is t equals 0. And then at t equals 4, we're at minus 25. And so we're going to do a dot at minus 25 and write at t equals 4. And at t equals 5, we're at plus 30. That's a big jump. So plus 30 is right here. Is that right? No, sorry, plus 15. Yikes. Plus 15, and that's t equals 5. Finally, t equals 8, so this is 5 to 8. We stay there for 3 seconds. 3 seconds where we stay at the same spot. Then at t equals 10, we are at 30, finally. So that's t equals 10. Then we race down to 0 for t equals 12. So at t equals 12 will be at 0. There we go. Then finally, use arrows to show the movement throughout the line. So this is the number line we've got marked, just like we should. Change this size to 1. Now we're going from 0 to 4. There. From 4 over to 5 to 8. That's there. We stayed there, and then we raced over to 10, and then we shot back to the 12. So there. That's question's done. Big check mark. Okay. Try this question. This one's more tricky. Kind of. We just got to really be careful as we follow the instructions. Pause it, try it out. We'll move forward very soon. All right, this one says this. We start at 30 meters north of your place. So this is a sequential story. So I'm just going to start plotting right from the beginning. We started 30 meters north of our place. Well, let's look. This is displacement north. So 30 meters north is right about there. I'm going to make this a bit bigger. 6 right there. Good. That's where we started. Okay, we don't have to start at 0, 0. We didn't start at 0, 0 here. We started 10 meters south or left. Here we're starting north, 30 meters. And other place, and we walk 2 meters per second for 10 seconds. Well, that's interesting. How far did we travel? We know we're at 10 seconds, so that's over here. This is 10. But how far did we travel? Well, here we've got a velocity right? So let's think about this one. We've got a velocity and we've got a time. And we are wondering what our distance is. Well, right? That's our question. Well, our triangle would say that v equals d over t, right? And we've got a v and a t, and we want the d, so we do v times t. And what do we get from that? We get that d equals our v of 2 times 10, which is 20 meters. Okay, so that's good to note. We've traveled 20 meters. All right, and so let's take our next dot and let's place it here at 20 meters south, right? We've been traveling south. And so what's 20 meters south? Well, up is north, so south, so we should be at 10, and this took 10 seconds. So it took 10 seconds to go 20 meters south. So we go down 20 over 10 seconds, and here's our next dot. Boom. All right. And this was a constant speed, so we're just going to take a line and we're just going to connect the dots. This one's done. We immediately change our speed and we get home in 2 seconds. All right, so we're assuming 0 is home. And in 2 seconds, we got to get home. Boom. All right, that's pretty simple. And we changed our speed, so it's another constant speed, so we just connect the dots. And now we sped up a bit, but that's okay. We're at home, now what happens? So this is done. There, we wait at the door for 5 seconds looking for keys, realizing we forgot them. Okay, well, for 5 seconds, that's until from 12, 5 more to 17, and we are just waiting at home. And so this is not moving, staying at home. That's what it looks like. Not moving. Our distance is not changing. Nice. We're cruising through this. We turn around and we go 30 meters north in 6 seconds. Okay, so we're going back to 30 meters north because we forgot our piece, so we got to go get it again. So 30 meters north in 6 seconds. So we're at 17. So we go 1, 2, 3, 4, 5, 6. Okay, 23. 17 plus 6 is 23. And we got to get at 23. We go straight up to 30 meters north. So we're back up here. All right. And it looks like it was a constant speed. And so we connect the dots like that. Sweet. We're doing this. If you think you're getting it, well, we're doing, it's at any point. Pause it and try it on yourself. We accelerate towards our house for 4 seconds, traveling 20 meters. So towards our house, we're moving back down, and we move 20 meters again. This is looking very similar to this, but this time we're accelerating. And so 4 seconds, we're at 23, so that's 27, and we need to make it till here. But the thing is, we are accelerating now. Okay, so what I want it to look like, accelerating, means this is stopped, right? It's flat. We're not stopped. This is moving very fast. We don't want that. This is a constant speed. We don't want that. We want to go from stopped and get faster. A curve like that. Beautiful. This is perfect. And so we accelerated towards our house for 4 seconds, traveling 20 meters, done. And then we slow down to a stop over 2 seconds, getting to our house. So 2 seconds is here. And we have to slow down along the way. And so what slowing down looks like is we're going very fast and we get slower. So our curve goes like this and we come to a stop. And then finally, and so that is done. We crushed it. And so we did that. Notice I had to draw those curve. Now we take 1 second to unlock the door. And so we don't move over that second. So my last point is there. And I put in a line. Nice. There's our beautiful graph. That's it. We followed the instructions, so we did each step, and we made this graph that represents this motion. Okay, big idea here. There's slopes with speeds. Okay, each slope has a speed, and we can draw acceleration as curves, speeding up, slowing down. Okay, speeding up is like getting more steep over time. Here it's getting less steep over time, so slowing down. Okay, try this question. This is the last one, I think. Yeah, there's an extra page just for fun. There's nothing there. So just pause it, try this question, and then we're going to work through it together. Okay, this question, between what times was Jared not moving? Okay, remember from this question, not moving looked like a flat line. All right, so where do we see a flat line here? Well, here to here is a flat line. And so those times are 5, make this smaller. That's between 5 seconds and 8 seconds. And so what we're going to write is between 5 and 8 seconds. That's it. What was Jared's largest constant velocity? Okay, so here he's accelerating, but there's no constant velocity. There's basically this one is constant velocity from 0 to 5, and here is another one from 15 to 20. But this is much steeper, so this is definitely his largest constant velocity. And so what was it? Well, in order to find velocity, our triangle says that we need two things. To find the velocity, we need the distance, and we need the time. And so what's our distance? We went 4 meters. Okay, and how long did it take? 5 seconds. Okay, you see we go from 0 to 4, that's 4 meters, and it took 5 seconds. So this is a 4 meters up and down, and this is 5 seconds, and that's a distance and a time. And so then our velocity is, we're going to do this down here. Velocity is going to be our distance, which was 4 meters divided by the 5 seconds, and we get this equals 0.8 meters per second. It's his largest constant velocity. What was the total distance Jared traveled? Okay, well, Jared started here. He went up 4 meters. He stayed there. He went down 4 meters, so that's a total of 8, right? So he went up 4 meters, down 4 meters. That's 8 meters so far. And then he went down another 2 meters and then another 1 meter, so plus another 3 meters. And he traveled 11 meters. All right, and so we can write that down here. What was Jared's total distance traveled? 11 meters. Now, at the end, how far was Jared from where he started? Well, he's not 11 meters from where he started. He started here and he ended 3 meters south. And so how far is Jared from where he started? 3 meters south of where he started. And we can see that just by looking at the graph. He started here and he ended up there. We don't even care how he got there. Took a roundabout way, but that's where he ended. What was Jared's velocity at 17 seconds? Okay, well, at 17 seconds, that's right here. How do we find the velocity at a single point? Well, he's on a line and he's traveling at constant velocity this whole time. So we just have to know, what distance did he travel? Well, he traveled 1 meter, right? Over a period of how long? 5 seconds. Now we have a distance and a time. We can find a velocity. And so what we're going to do is his velocity was, he was in the middle of traveling 1 meter in 5 seconds. And so that gives us a total of 0.2 meters per second. And specifically, he was going south. Right? He was going down. Honestly, here, we should have said that he was going north, because we knew that. And if we know the direction, we should state it. Oh, 6. When is Jared speeding up? When was he speeding up? Well, I know he's moving down, but this is the section he's speeding up. His velocity is getting faster. He instantaneously speeds up at the beginning like he's going fast, and then he stops. And so technically there's some slowing down here, but this is the section where we see a curve on the graph between 8 and 12 seconds. We see that his speed is increasing. All right, and so the answer is between 8 and 12 seconds. Is that right? 8 and 12, yeah. That's when he's speeding up. And when is Jared moving south, but still north of the origin? When is he moving south? That means his movement needs to be down, but he's still north of the origin, means he's still above the origin. Well, here he's moving north and north. Here he's not moving. Here he's moving down and north. Oh, and he's moving down and he's south, moving down and he's south. And so it's just this section. It's the same as the last one. So again, it is between 8 and 12 seconds. That's when he's moving south, but north of the origin. All right, that's all the questions. If you have more questions, feel free to email me. Go do some graphing questions on practice to see how you're doing. Check the answer key, and if then you identify you're still not getting it, like feel free to rewatch this or practice more questions or ask me for more help. And I'm always willing to help. You might have to email me, and I'll try to get back to you as soon as I can.